Hello and welcome back for another episode of Disc Golf Physics. I'm Joe Johnson. I'm a physics professor at Mercyhurst University and a disc golfer. So it's been a while since I put one of these out. I thought it was about time to make one. Recently I saw a video of a pro and he was asked what's the best piece of advice you can give to a new player. And he was talking about the power pocket and how important it is to get that disc in this power pocket as you're pulling through to get the power to transfer from your body into the disc in the throw. And I wanted to look at the physics of why that was. And I noticed that if you look at the throw from above, this power pocket looks an awful lot like a bullwhip as it is snapping through Indiana Jones style and coming to the end. So the bullwhip makes this arcing motion as it's coming through, getting smaller and smaller. And I wanted to look at how that compared to the arm motion of the throw and think about some of the physics behind why it is the way it is. So that's what we're going to talk about today. To make the comparison between the two motions that I just mentioned, I had a friend, my friend Stan, did a drone video of my throw from above. Accelerating through the power pocket, and the video quality is great. So thanks, Stan. Shout out. Thanks for the drone. Really appreciate that. Here we'll look at one more. Super cool to see. And then I took a video myself of my friend Brad. You can remember him from a past disc golf physics video, and he's using that whip I just showed you and snapping the whip, getting a good crack on it. And then I put those two things side by side. So, all right, we can see as we slowly progress through that the motion, while different, does have some marked similarities. And I think the physics translates pretty well. Specifically, we're going to be talking about conservation of momentum. So you can watch, all right, right here. Oh, too far. Right there. You can see how the whip is making this rounded arcing motion. So as this part becomes straight, the length of whip that is left gets smaller and smaller and smaller. Similarly, my arm is making this arcing shape. And as I'm extending through my throw, the amount of my arm that's moving is smaller and smaller and smaller, moving from bigger levers to smaller levers in my arm. So as we pull through till we get to the extension and the snap through. So that is the point where my disc is in the power pocket. It's loaded and ready to pull through. So we can watch them together. And I did another one. That one you're only seeing the end part. Oh, that's a really good view of the arc in the whip as it's coming through. And it's right in line with the arc of my arm as it snaps through. Snap through. So I took that video of me from above and I put it into my Logger Pro software and I tracked the motion frame by frame. We can look frame by frame as the disc is moving through space. And just a little quirk of my my timing and my throwing motion, I put the disc out in front of me. So this part of the graph is where I'm moving forward, and the disc is moving forward even though my body's not really moving very much. This part of the graph is where the disc is moving backwards relative to my body. That's my reach back portion. And then right here is the point when I'm at full extension and start drawing the disc forward. This is a velocity. We can look at the position as well. So reaching the disc forward, pulling it back. As my body's continuing to move forward, I'm moving around the disc. And then this is where I'm pulling through. And we can see that in this frame by frame. The part I just showed up till this point is when I'm extending the disc in front of me. That was on the advice of Ricky Steeler, a pro out of Buffalo. He said it'll help with my timing, and it turned out it did. So thanks for that advice. This part that we can see as the disc is drawn back, and I reach back with an extension behind me. I've moved around the disc and extended the disc backwards. That's this part of the graph right here. And now this is the part that's actually of concern. Notice that this part of the graph is curving. It's not a straight line. It's the distance between these dots is getting bigger as time goes, which means that the slope of my graph is increasing, which means I'm accelerating. My velocity is changing. And we can see that if we switch over to a velocity graph. So here the velocity of the disc is relatively small and negative, meaning it's going backwards relative to my body. It's moving in the negative direction during that as my body's moving in the positive direction. And then at this point right here, it's accelerating forward, and the point at which the slope of this graph is at a maximum is where my acceleration is the maximum, and we reach a velocity right here. This is the coolest part, I think, actually. It has nothing to do with the topic for today, but those three dots are the last three frames. As I'm accelerating the disc forward, we can see each dot is getting farther apart and the velocity is increasing until my point of release. That first dot right there is the first dot when it's not in my hand and I'm not pushing on it. When I'm not pushing on it, there's no force. No force means no acceleration. No acceleration means the velocity line becomes flat. And air resistance is actually going to start slowing it down, but we don't have enough frames to really see that. So it's on the screen for 1, 2, 3 frames before it's gone. So 3/30ths or 1/10 of a second, because each frame is 1/30th of a second. And there it is, it's gone. So we can see from this velocity graph that the largest slope, the largest change is right at the end, right here, this portion of the graph. Those 3 points, the last 3 as I'm accelerating the disc. Now, why would that be the largest acceleration? Why is my velocity getting bigger faster at those points? It has to do with the conservation of momentum. So before we get too far into talking about conservation of momentum, let's review what momentum is and a little bit about it. We've talked about momentum at least a little bit in past videos, but momentum, we use the letter P to represent it, and it's a vector quantity, so we put a little arrow on top of it, equals m times v, where v is the velocity and m is the mass of the object. So if I've got a car driving and I hit the gas in the car, I speed it up, the faster I'm going, the more momentum I get. But if I'm driving a big heavy truck, it's going to have more momentum than a car at the same velocity but a different mass. So momentum depends on both mass and velocity. Changes in momentum, delta P, is called impulse, and delta P equals the force applied times the time over which it's applied. We made a video about this before. Sorry if my handwriting's bad. That says delta P equals F times T. So the amount of change of momentum you get is going to equal the amount of force you apply multiplied by the time over which you apply that force. So it's one of the reasons why you follow through in both baseball or traditional ball golf and in disc golf too. I want to maximize the amount of time that I'm applying my force. The longer that I apply the force to the disc, the bigger the change of momentum is going to be, so the larger the final m times v is going to be. The mass is fixed. For this one, it's 176 grams. It's not going to change in the throw, but I'm going to increase the momentum by applying a force over a time. I get a change in momentum because of that. A different consequence is that if there is no outside force, if F is 0, then there won't be a change in momentum either. So if F is 0, then delta P is 0. No change in momentum if there's no outside force. So during the throwing motion, if there are no outside forces, the total momentum has to stay the same. All right, keep that in mind. Put that in the back of your head. For the bullwhip, as it's moving, I apply an outside force to accelerate it, but once I've accelerated it, the bullwhip is moving, and it's moving this whole mass, the whole mass of everything involved, the entirety of the whip. As it is going, it gets straighter and less of the whip is moving. So as it is extending out, the amount of whip that has a velocity is getting smaller and smaller and smaller. As we approach the end of the whip, there's much less mass. If the mass goes down, but the momentum stays the same, then the velocity has to go up. So if I go back to my equation here, P equals m times v. If P isn't changing, it's constant, it's staying the same, it's conserved, and the mass that is moving is decreasing, the only way that's possible is if the velocity increases. The velocity's got to go up. So as the amount of whip that is moving gets smaller and smaller and smaller, we get less and less and less whip, then that little tiny end gets going really fast. In fact, it goes faster than the speed of sound, which is why you get a cracking sound at the end of the crack at the end of the whip. Well, looking at that video with the comparison, my disc golf throw, while not identical, is similar to that whip motion. The power pocket is very similar, looking at it from above, to the arch that is formed as the whip is extended. So as I extend my arm, less of my arm is moving, and the mass of the thing that's moving, my arm and the disc, gets smaller and smaller and smaller, which causes the disc to be moving faster and faster and faster. So conservation of momentum plays an important role in why that power pocket is so important and how we get that snapping motion as we're throwing and accelerating the disc to the point of release. Hope you enjoyed it. Hope you learned something. Thanks for watching.